malware 3D visualization. Please give him a warm round of applause.
All right, good morning, everybody, and let me just thank you for either crawling out of your hangover and coming to see me again for the third year running, or for not going to the party last night. That's good. So I'm here to talk to you about malware visualization in 3D. So let's just go ahead and get started. So this is what's on my list of things to talk about. I'm going to try and introduce the problem space that I'm working to solve here. Specifically, why reverse engineering is hard, assuming you're not Frank Goldwyn. But and I'd like to talk to you about malware analysis specifically. So I'm going to establish the goals of the visualization, and I'm going to talk a little bit about my tool Vera, which I've presented on before, but I'll reintroduce it and then talk about some new features that we have. And this is going to be a fairly demo-heavy talk, so just take a small moment of silence in deference to the demo gods.
Any special glasses or something?
Yeah, you do. You do. I mean, there wasn't a box of them. Phil, that was you. You're fired. No, you don't need special glasses or anything. So, all right. So go ahead and get started. So the reverse engineering process. This is just how I see things. So I know everybody else has their own way, but when I'm teaching people how to reverse engineer, this is sort of what I fall back on and try to explain as the overall process. So how many of you here in the room reverse engineer? Good? Okay. All right. So there's a fair number of you, so I'll try to use big words. So the first thing you got to do is set up an isolated environment. This is something like VMware. It used to be other things like Zen and Virtual PC or dedicated hardware of some sort. And this is just to protect you from when from when the malware actually does its infection. The next thing that's done, and I would say that this is a lot of what people who claim to do reverse engineering do, is they use tools like sysinternals and CW Sandbox and that sort of stuff. So it's basically just looking for any sort of state change in the operating system. Files that are written, registry entries that are changed, network traffic, and this is sort of the 90% mark for getting there. The next step is that if there's any obfuscation or hacking, this needs to be removed. There's a couple of well-known techniques that we'll discuss. Of course, there's a tried and true debugger, things like Saffron, Renovo, PolyonPack, and Ether. And then the next thing is to actually take the machine code and translate it into something that you can read. So it's a little bit difficult to actually take the binary and do that. I know there's some people that surely can do it, but I prefer to look at the text listing of it. So these are things like IDAPRO and OllyDebug and that sort of thing. So once we've got those, we get down to the bottom entry here, which is basically to identify a relevant and interesting feature. So this is sort of the hand-wavy portion of reverse engineering, and it's all experience-based. And so when I teach reverse engineering, we sort of go over these first few things, our first items, in roughly a day. But then afterwards we spend a lot of time on the last part. And a lot of this is experience-based. You just have to know or get a feel of what you're looking for and develop that. So as far as the overall process, when we're looking at code, most malware that we look at is compiled x86 assembly, although I hear that one fairly happy malware vendor recently got between 1 and 5 million infections on the Android store. So, and it would run if the Android battery lasted for more than 30 minutes. But, okay, I don't like Androids. Okay, so what we do is we start out with the C code on the left, and basically a compiler is going to apply optimizations to it and translate it into the assembly that we see on the right. And then optimizations and that sort of thing make this difficult, and so the total size for this 45 lines of C code is about 1,200 instructions. But when we're actually looking for the relevant portions of this to actually do the reverse engineering on, it's going to be about 118 instructions. So the question is, how do you find those 118 instructions in this pile of mess? So, and the answer is that much of this is boilerplate, and you got to do this. Okay, so the compiler goes to the right, and the reverse engineering goes to the left. And furthermore, you can obfuscate these executables. So you can take this code on the left, and the compiler does things like it takes out variable names, assuming that the debugging features are off, comments, if it had any, and the original structure of the code, and mangles it a little bit to what we're looking at. And then furthermore, what we can do is we can take the thing called a packer or any sort of other obfuscations and further jumble it up to make it harder to look at. And so what we're fighting against is information loss, especially for packing. As far as packers, I run the website Offensive Computing, and based on about 3.6 million samples, samples of those that are packed, this is typically the breakdown, and primarily UPX is the most predominant packer that's out there, followed by ASPack, FSG, PECompact, and ASProtect. So does anybody have an idea why UPX is roughly 50% of all packed malware?
It's free.
Free? Okay, free is a good answer, but free. Anybody else?
Open source, you can come up with it.
Right, it's open source and you can F with it, and also
Everybody uses it, even for legitimate purposes, like Java.
sort of, yeah. There's an interesting side note about that, but I'll try not to get derailed. So the reason that everybody uses it is because it's one of the only ones that actually works. If you start looking at some of these other boutique examples of packers and stuff like that, especially when we start getting into the little sliver section over there, you know, the ones that everybody knows about, that's a fairly easy thing to automate, and there's lots of things that have been talked about how to automate them. But when we start to get into the little end of the dregs of this, we get into the manual deobfuscation. And so this is stuff where somebody has actually manually written a tool from scratch, usually handwritten in assembly, to go through and unpack this. So, and that's where you get comical mistakes too, but alas, it's not part of this either. Okay, so Vera, this is a visualization tool for reverse engineering. It's specifically made to handle the quick understanding or cognition of a program. Basically, this is all a force-directed graph, so you mathematicians in the audience asking what the x and y axis are, they don't mean anything. Basically, it helps you determine where to start the reverse engineering process. And the whole idea behind this is to cut down on the reverse engineering time and make unpacking a little bit easier. So I'll go through a little bit of it. So this is the 2D interface. This is the 0.3 release. This is a network trace of the Notepad executable as it's running. I believe that's right. And so we start out in the lower left-hand corner. The blue, or dark blue flag indicates the start of execution. And then as we see each instruction execute, we just make a note of that. And then the results of that are built into a directed graph, which is then applied to a force-directed algorithm through the Open Graph Display Framework, and then displayed. So this is a nice navigatable interface, so you can actually zoom in here and get an idea of the overview. So the basis behind a lot of this is that you can find loops, and loops come out fairly easily, and other programming constructs. So since this is looking at the dynamic behavior of what's going on inside of the executable, we've got the loops. The yellow colors indicate normal code, and I'll talk about what normal is in just a minute. And the green loops indicate that there's a API call that happens. And then the more times a series of instructions are executed, the thicker the lines are drawn, and we go through it. So if we zoom in here, this is basically the end result of what we're looking for. You can see this is inside the init term code of a normal Windows executable. But this is just like a simple for loop, and actually it's the Windows equivalent of processing the main arguments to a program. So you see the get main args, and then an init term, and so forth. Excuse me. Okay, but zooming in on other parts of the graph, you can actually start to see other structures. So being that this is Notepad, it's actually going to respond to events from the executable, or from the user that's going to be typing in. So you would expect there to be a, if they press Control and X, that means they want to, cut or whatever. This is going to be inside of a switch statement that we're going to pull out. So inside of here, we've got a switch statement where we've got a lot of things going towards that central node and a lot of fanning out. So this is a basic area here. The colors, what they mean is basically these are meant to help you with unpacking, and I'll illustrate this in just a moment. But essentially, yellow means normal, uncompressed, low entropy data. And so for the entropy calculation, I'm using the Shannon entropy or P log P. Dark green means that there's a section that's not present inside of the executable module. Either it's a DLL or an API or something. Light purple means the size of raw data is 0. Dark red means it's a high entropy, so anything above a 7.5 I mark as dark red. Light red means that the instructions are not in the original packed executable. And lime green means the operands don't match. So you had a question? Yes?
Did you pick those colors because they helped in particular with your analysis, or are they basically random?
Well, okay, so the question is, did I pick the colors because they help with analysis? And I would like to say yes, but you know, the randomness is sort of there. But you know, being a typical male, I have no sense of color or aesthetics, so I won't claim that they look good. But that was sort of the end goal. But yeah, there is an alternate set for those of you that are colorblind, because a friend of mine took a look at this and said that's great, but everything's brown, except for one of them. But anyway, so there is an alternate set, and you can get this. But for this demonstration, I'm going to use the ones that's originally made. And so I hope that you can see some transitions if that affects you. My apologies. Okay, so to actually reverse engineer this or apply this into your malware reverse engineering process, you basically run this trace inside of a virtual machine. So originally we started out with the Ether system, written by Artem Dynaberg, and Ether's awesome and great and that sort of thing. But Ether's gotten a little complicated lately to install, and most reverse engineers that I talk to, they're very comfortable with using the VMware type approach and actually getting their information that way. So anyway, there's a new Intel PIN module that was released last year that collects all this information for you. It makes it a lot easier. So you don't have to have a big Ether infrastructure or a custom installed Zenbox on an old version of Debian that's not supported anymore. Okay, so this is KubeFace. We start in the upper left-hand corner, and you can see that there's a dark red portion or a dark area of executables. This is actually the packer. And I'll go into how you actually determine what is the packer in these a little bit later, but this is what a UPX packer looks like. When you generate these graphs, there's going to be different layouts, but essentially the overall form or the types of loops are going to be pretty much the same. So if we look at the, I have a pointer here, but if we look at the upper left-hand corner, there's a main set of thick loops right there. That's the decompression portion of the UPX packer, and then the secondary loops are the import restoration. And then finally we end up at the transition, which is the original entry point. And essentially the transition to the original entry point is going to be the new colors that show up. After that, towards the center, there's going to be a long initialization. Okay, look up here.
Yeah, this is really hard to follow on the back.
Thank you. Yeah,
sure.
Oh, thanks. You're awesome. Okay, so this is the UPX packer. This is the decompression point, and this is basically the import restoration code. And then we've got the initialization, and then right here there's a transition between the red and the light purple portions. That's the original entry point. Basically what you're looking for in any of these unpackers is a transition, or the last transition to one of these colors. So in this case, we've got this light purple section, which if you remember is where the data is allocated in the original executable but not present. So when the executable loads up, it decompresses itself into this area that it's set aside and then starts executing it. And then we have the main execution. So this little initialization portion is going to be something that you see a lot inside of Windows executables. This is standard compiler boilerplate that's going to find the standard compiler boilerplate that you'll find. This little pigtail here is going to be another indicator. And so pretty much from about here on is where you can start looking at the executable. We've got the initialization. Now we want to start finding various areas of the executable. So each one of these long-running strands right here is going to represent either a function or an area of functionality. And basically, there's an interface where you can right-click and find it inside of IDA. Okay, so we've got the DLL procedure loader for handling the imports again for the secondary method of obfuscating imports. And then we've got the service installer and then the payload startup. And of course the file injection. But KubeFace behaves a lot differently when you actually get it installed. So when it's started as a service, it has a completely different execution and behavior. We've got the initial UPX packer, which is going to have some of the similar dimensions that you'll see. We've got the original entry point, which happens at the same place. The executable preamble, which is going to contain the initialization code. And then things get a lot more complicated. So if we look at the previous example versus this example, it's a lot more going on inside of here. So that's just a cue that lets you know that something else is happening. And again, we're just going to look for these long-running loops of execution, find these various places, and then using this, we can start identifying where things are. So if you remember KubeFace, if anybody has gotten hit by it or have relatives that have been popped by it, it's your ultra-conservative mother-in-law who posts pictures of some girl getting her butt spanked about something or other. That's the common thing for KubeFace, and we all giggle and then go on. But anyway, it's basically trying to spread itself and convince people to click on it. The primary attacks are against Facebook, MySpace, Bebo, those sorts of things. So it's all the major ones. We've got the command and control code to call home, and then it's Google search to actually work with it. Okay? All right, but that's all old stuff. So what I would like to talk to you about now are some of the new features. So, somebody else? All right. Kind of afraid of that noise. Good. All right, so I have here a picture of a standard reverse engineer in his normal everyday setting. And I'd like to introduce the 3D features to talk to you about. So the reverse engineer is going to get ready. So we got this here. So let's pull this down. Give me just a second to get this started up. Awesome. The demo gods have found me lacking. Hold on. Okay, so what this is it's exactly the same sort of tracing mechanism. We're not picking out anything else. But what we're using is this system called UbiGraph, which if you've ever played with it is an absolutely fantastic 3D layout algorithm. And I'll talk a little bit more about that and get proper credit. But inside of the system, you can actually start the maneuvering around and navigate, and you can actually set it to spinning and that sort of stuff. So there we go. That's it. It's a little bit bright here to see it, but essentially what it is it's a 3D force-directed layout placed on the Fruckham and Reingold calculations with a little bit of smoothing. And we can actually do some navigation, so it's a little hard to do it sideways, but you can see some of the original structure that's going to come inside of this this program here. But this is the initial KubeFace infection system. And this is how it's installing itself. So we've got this various beach ball structures. Really just, there we go. So you can zoom in and out. You've got the start area here. We need more lumens. Yes?
So distance between points represent distance in memory.
The adjacency of 2 points that are connected by an edge means that there was consecutive execution between the two of them, but the distance doesn't actually imply anything other than the spring and attraction forces. Okay, but the start, this over here is basically going to bring this out. Okay, so this is the 3D view that we've got, and we've got the same basic interface as we have on the other system. So let me show you some other another set of graphs. Okay, so this is the notepad graph that we looked at previously. Essentially what the interface is to UbiGraph is an XML RPC. It has, if you've ever done any sort of graph layout, this uses the exact same things that you would use to basically lay out a graph initially. And those things. You add your edges, you add your vertices, and then you tell it how it's connected. And then the UbiGraph system actually goes through and makes a series of good decisions about how to display it. Okay, so this is basically the exact same thing that we're looking at, that we were looking at previously. And you can navigate through it. So one of the problems with UbiGraph or any of these 3D visualizations that I actually ran into is that you get into a situation where they actually sort of look good and they're crowd pleasers. Usually, well, like management gets really impressed with this. But when you start looking at it, they get complex really quickly. And so the advantages and disadvantages that you find versus a 3D visualization versus not are somewhat different. So I'm gonna show you a threat that was basically an internal one that hit us from a targeted group. We'll look at this. Okay, so this is again taking all the traces, executing through them, or executing them inside of UbiGraph and then building them out. We start to build these connections here.
Now, do the colors have the same meaning as what you've given it for?
Exactly the same, yes. So we start to build this, but the problem is that inside of here, you sort of have to go through and mess around with this to actually start building any sort of idea or mental map about what's going on. And what's really nice about the 2D system is that you don't necessarily have to be as involved with it as that. You can do a much more passive look at it. Okay. But this just gives you an idea of some of the other things that were going on. But it's still very complicated to look at. Now, if we look at the, shut this down here, and we're just going to look at the 2D version. Hey, calm down.
What do each of the stars represent? If you want to, you can actually answer.
That's right. I don't know. Steve Jobs likes stars, I guess. So. Get out of here, jerk. Okay, so this is the old Vera GUI, and this is essentially the same view of this. And this is a common critique that I have with a lot of the 3D systems, is that they, the 2D ones tend to convey a lot more information a lot more clearly. So that's basically it. It's a lot easier to pick this out versus a 2D system. However, the screensaver aspect of the 3D visualizations is somewhat improved. Okay. Good, okay. So notes on the 3D layout. This is again UbiGraph. There's a force-directed system, which is a vlog-v algorithm, if that makes any sense to you. Really good threading. The other issue is that it's only for Mac and Linux, which has become less of an issue these days now that IDO works on Mac and Linux. and it's going to be integrated into the Vera GUI for export. If you're interested in UbiGraph, there is a good talk from, or a good paper from a guy named Todd Veldhuizen. Maybe I pronounce that. But for the life of me, I can't find him. I, of course, have emailed him. I've tried to track him down. I've tried to track him down through his advisor. I knew a guy who was in Canada where he was supposedly living, and he was not home. And that sort of thing. So, Todd, if you're listening, if you would, please contact me. There are people that would like to give you money. So, if you're looking for the address, it's this UBID lab, and we'll look it over. It's actually very, very good. And there's a great paper about it, which gives you all sorts of stuff. So if you're into graph drawing, okay. So let's get into temporal visualization. So these are the new features of Vera that we're gonna start looking at. So why is time important to reverse engineering? So understanding the flow of events usually it helps to reconstruct what the program's doing. So when I get queried by a customer who wants to ask what's going on with a piece of malware, they want to sort of know what's happened at what time and what's happening. So in the case of Mebroot, if you guys remember this one, Mebroot was one of the first master boot record infectors that came on in a long time. So there's an initial 30-minute busy loop that happens, and usually when you run it, it just basically chews through your CPU, and you don't have much to do with this. So the question that you ask yourself is the malware broken, or is it actually working? And basically you want to check and see that it's functional and persistent. So what I did is I took a trace of it, ran it, and it turns out that yes, it does work due to the complaint that I got from my IT staff about me being infected with malware. But anyway, complicated samples can get obfuscated very, very quickly. So what I would like to do is show you a couple examples of these tools here to just illustrate a little bit of it. Yes, note to self, I will change my background before presenting it for you guys again. Okay, so let's take that same coop face trace. It's going to take a little bit of time to load up, but this is essentially the exact same thing. If we explore around inside of this trace here, we've got the start section, we've got this high entropy area, so it doesn't look like it's actually a known packer. But inside of here, you can see that there's some interesting things. Like one of the things is that there's an execution to a null memory address. So if you've ever looked at a piece of malware, one of the tricks that they'll try and do is they'll generate exceptions and try to crash the program to get it to go. And one of the things you can do is by dereferencing a null pointer. And so what CoopFace does is it uses the structured exception handler to instigate one of these bugs and get around it. But then there are two branches outwards, and then we've got the actual initialization and installation portions of this. But one of the things you don't really get a good idea of is where is the temporal action, or like what happens at what time. So let's go ahead and do that. I'm going to run it. Basically what I've done is I've taken a trace, I've taken a log of everything that's being executed, and I'm watching it as it's doing there, and I use this to build an animation. So we'll push the play button now. And you can see that there's a little portion of execution that's being filled out inside of the main visualization, so you can see where the program is headed, what's being executed when, and it gives you a better idea. You can actually navigate and see what's going on. So it's a little bit difficult to see, but it's inside of there. This isn't necessarily the best example of this. This is a fairly simple algorithm for actually developing the animation portion. But where things actually get a little bit more complicated is when you're looking at a sample that is based on some actual commercial code. So I'll go ahead and bring that up. So we have this document that was sent to us. We're basically trying to get people to click on it. Give a little load here. And essentially, this is one of those things where it says, there was a targeted attack to somebody inside of our company that was sort of trying to figure out what was going on. And we get this right here, right? So in the visualization field, this is something that's called a yarn ball. It's not very useful, and it's a little bit difficult to actually figure out what's happening where. You can actually zoom in inside of here and get a little bit better idea of what's happening, but for the most part, it's not going to be a consistent view. Okay, but with the animation, restart this here. With the animation, you can start picking it apart and getting the actual information that you need fairly quickly. So, let's go in here. So the trace files result in a little bit bigger data, so it takes a little bit longer to load. There we go, that even looks better. But when we're trying to track what's being loaded when, we can use the animation and we get a little bit better grasp about what's going in here. So you can see where it's actually executing inside of this area and the areas that it's actually running through. So this allows you to narrow in a little bit closer on what's available inside of here. Okay. All right, so that's the animation view, and you can use that. Primarily, this is important, especially when you get into reverse engineering commercial software. Commercial software tends to be a little bit more difficult than malware to look at. There's a lot more code to look at. Question in the back.
Yeah. Have you thought about when you do the technical display as you go through it, to get rid of the yarn ball, just kind of like display it as it happens,
Right. Yeah, I mean, there are some, so the question is, have I thought about displaying each node as it's being executed so that it's a little bit easier to see? Yeah, that's definitely something that's in there. There's a couple of trade-offs that I'm working through. It'll be different in the final release, but essentially what we're trying to, or what I'm trying to fight with is that if you just do a one-by-one visualization of everything that's being executed, there's an awful lot of loops inside of here, and you end up staying inside of the loops for a little while. So I'm just trying to get past that and still provide some sort of idea about how things are executing. So typically what I'll do is I'll just only go through a loop once and animate that. I hope that was a close question. Okay. Okay. So the next thing is the search feature. This is a commonly requested feature based off of what we were looking at. Basically, people, it's a really good interface to go from Vera to the actual IDA GUI, but also vice versa. So this allows synchronization there, and it reduces some of the hunting and searching for a lot of the APIs, and it helps out a little faster code discovery. I'll show that in a little minute when we start looking at the unpacker. Okay. So as far as visual unpacking, if you know how to unpack a file, it's fairly trivial to actually be able to figure out how to do it. There's some known techniques using the push AD and pop AD and that sort of thing. Where you get into a lot of trouble is when you have an unknown packer or something that's not necessarily unpacking code or obfuscating, and you need to figure out what's actually happening. So I'm just going to go through an example of how to use this on a completely new custom-written packer for the Poison Ivy variant. There's automated methods. Again, Ether's awesome, PolyUnpack, those sorts of things. They do a really good job, but this is sort of for when those fail. So as for the code here, we've got the architecture of a packer. We've got a malicious packed executable. So typically we start out, there's a little, the packer starts out with the initial compiled code, and then there's a small unpacking component that's basically taped on at the beginning. And the entry point is patched to go to the unpacking code. As the unpacker executes, it's going to decode and then finally pass everything back to the unpack code. And so what the fundamental flaw that we're exploiting inside of any sort of unpacking system is that we are waiting for the unpacker or the decompress code to actually pull out the CPU instructions, because an Intel CPU can't actually execute anything but valid code. All right. Some other notes about packers. It's extremely rare that malware is written in pure assembly. You saw this sort of at the beginning of the 2000s and late 90s and that sort of stuff. That's when there was some really clever methods for writing a piece of malware. Certainly on the demo scene, a lot of those are custom written, and they're going to be pretty highly tuned assembly. So you'll see a lot of those inside of there. But most malware, especially the commercial malware that's going out there and trying to steal money, is a commercially written piece of software. And if you look inside of it, you're actually going to find software quality and that sort of thing, test harnesses and that sort of thing, which means that it's written by a compiler. So after the compilation process and after the testing process, you'll have a software that's ready to be deployed, and then these obfuscations are added on past that. So UPX is one of them that's added on and so forth. Okay. So if we look at, this is sort of a display of some of the packers that are actually outside of there. We start out with our packer on the bottom left-hand side at the start. This is the UPX packer, has the same sort of overview of it, but there's some standard functionality that exists inside of here. But we've got a good transition from the dark red to the light purple. And again, dark red is high entropy, and the light purple is the size of raw data equals 0. OEP is a transition from the dark red to the light purple, we can find. ASPAC, this is another one here. ASPAC is actually low entropy code as far as what's going on, but it decrypts everything in place. And then we have a final transition, a final transition to the unpack code, and then we start the actual execution inside of there. FSG, which is another one of the popular ones. Again, we have the small loops right here. We have the import restoration code, and then the main executable being run here. This, aside from the colors being mismatched, this is very, very similar to the UPX unpacker. As a matter of fact, this is one of the slide lines. Okay, so as far as staged unpacking, in this case, we've got a start component here. This is where we start inside of code that's outside of a section that does initial decompression. This encrypted code is something that was compressed or encrypted before, and then finally got here. So this is basically a staged unpacker, which is mu, before we actually get into the executable code. And then the final one I would like to show you is TLOC. TLOC is a fairly complicated one. We start out with normal code to do the unpacking and basically go through this process to unpack, decode itself, and then start re-executing sections. So it makes it a lot more complicated, but eventually we get through it and we're able to trace it. Okay. When we look at automated unpacking is essentially this algorithm. If you look at a lot of the research that's been out there, the first thing that we're going to do is that we need a system that's going to watch and look at what the actual instruction's executing. And essentially what we're looking for is the instruction writing to memory. If it's writing to memory, then log it. And then the very next step we do is to check and see if that is EIP actually executing inside of a previously written address. If it is, then it's going to dump the process. And this is basically the entirety of how a lot of the automated systems work. So you need a system that actually tracks memory writes and executions. And once you've got that, you've pretty much got a system to do this. A lot of the differences among the solutions that are out there are basically differences in how you monitor. All right, so as a reverse engineer, one of the things that I do is I actually have to unpack a fairly robust set of other examples. So what I would like to do is I'd like to show you how to use Vera to accomplish this. So we're just going to start up Vera again. Get the mouse on the right side of the screen. Okay, so what this is it's a copy of the Poison Ivy variant. And over here on my virtual machine, I have my Elite reversing setup. You can tell because it has a cool picture in the background. So I'll start off, this is the malware downloaded fresh from Offensive Computing. If we start looking inside of IDA Pro, essentially there's not a whole lot to this. So the point of this is that this actually got into the unpack code, and a lot of this is not actually present. And